Here's a quick video to clear up the differences between the differential rate law and the integrated rate law that were brought up in class. Differential rate law is in the form of a rate. A rate is equal to some rate constant multiplied by the concentration of the reactants raised to some exponent, and this exponent is what we call the order in a reactant. It allows for us the ability to determine the instantaneous rate of a reaction given a particular set of concentration conditions. And note that the larger that the order of a reactant, the more sensitive the rate is to change in the concentration of that reactant. Now we can use this particular form, the differential rate law, to describe what's happening at the molecular level of a reaction. And this is going to become important when we discuss things like the mechanism of a reaction. And the mechanism of reaction basically is just how the reactants come together to make a new product. And we'll describe a little bit about that later on. The integrated rate law is usually, it comes in various forms, and those forms depend upon the order of the reaction with respect to the reactant in question. So the three that we discussed in class are the first order integrated rate law, the second order integrated rate law, and the zero order integrated rate law. And these are for first, second, and zero order overall reactions. And we use the integrated form when one wants to consider the time that it takes to get from one reactant concentration to another. Using the integrated rate law, we can ask various questions like how long does it take to react? What is the concentration after a given amount of time? What was the initial concentration, and what is the half-life of a substance? There's a table in your textbook, and I believe in the new edition, this chapter 13, table 13.2 is wrong. I believe it is now table 14.2 in the fourth edition of the Trove text. And my apologies for not having that. But what this does is this summarizes. It gives us, for a particular order, it tells us what we would expect the rate law to look like, what the units of the rate constant would be. It shows us the integrated form of the rate law. It also shows us what we would expect a straight line plot to look like for that particular case. A zero order reaction would have a straight line when plotting the concentration versus time. A first order would have a straight line plot when plotting the natural log of the concentration versus time. And a second order would be linear when we plot the inverse concentration versus time. And additionally, this table shows this thing called the half-life expression, and we'll get to that later on in class. Alright, so we've got two types of questions, and one is using the differential rate law and the other is using the integrated rate law. So the differential rate law we would use to answer a question like this. It says use the following data to determine the rate law and the rate constant for the following reaction. We've got reactant A plus B react to form C in the presence of hydrogen. And sometimes something like this hydrogen would be considered as a catalyst, and it can speed up the reaction. And even though it's not in the reaction equation, we state that it does participate by putting it over the arrow. And so now what we want to do is, using this data, try to determine the rate law. First the rate law, and then the rate constant for the reaction. Now remember in class I said that if we wanted to solve for the order of A, we'd want to pick two trials in which A is varied, but any other component is held constant. And what first comes to my attention is trials 1 and 5. We can see that we're varying the concentration of A, but B is held constant, and the concentration of the hydrogen ion is also held constant. So in that case, we can compare the two rate laws for the two trials, 1 and 5, and solve for the order in A. And if you recall, we would say that the rate of trial 1 over the rate of trial 2 equal to the rate constant times the concentration of A raised to some power, I'm going to say X, times the concentration of B raised to some power, Y, and times concentration of the hydrogen ion raised to some power, Z. And the same thing, my apologies, this is trial 5, K times the concentration of A, the concentration of B raised to the Y, this should be raised to the X, concentration of H raised to the Z. Now, since B is constant, if we're comparing trials 1 and 5, B is constant, hydrogen ion is constant, and remember that the rate constant is constant. So now we've got that rate 1 over rate 5 is equal to A to the X power over A to the X power. And we can substitute, and we would say that 18.8, and I'm going to leave out units, but there'd be molar per second, divided by the rate 5, which is 21.7 molar per second, is equal to the concentration of A in trial 1, which is 0.30 molar, over the concentration of A in trial 5, 0.40 molar, and this should be all raised to our power of X. Now we'll use the log to extract the X, and in this case I'm going to use the log base 10, and so I've already evaluated this value, and we end up with the log of 18.8 over 21.7 is equal to 0.866 equals X times the log of 0.3 over 0.4, which is 0.75. This should have the log in here as well. So now we'll say that X is equal to the log of 0.866 divided by the log of 0.75. And if you put that in your calculator, you should come up with something like 0.5. So that means that X, the order in A, is equal to 0.5. So we'll remember that. And let's go on and solve for the order in B. So B, we're going to take two trials where the concentration of A and H are held constant, but we vary the concentration of B. And in that, the first thing that I see is trials 1 and 2, where we've held A constant, H constant, but we're varying the concentration of B. And we can use a similar approach, noting that the concentration of A is constant, concentration of H is constant, and that K is a constant, so that we can say that the rate 18.8, that's molar per second, divided by 37.7 molar per second is equal to our difference in concentration, 0.050 divided by 0.10 molar, and those are raised to what we'd said was the Y power. So we can solve for Y by taking the log of both sides, and we get the log of 18.8 divided by 37.7, which is the log of 0.499 equals Y times the log of 0.5. And if we treat this similar to the way we treated the last one, we come up with Y is equal to 1. So now we know that that the order in A is 0.5, the order in B is 1, and all we need left is to find the order in H. So for H, I see we've got two possible data sets or trials in which we could use to establish the order in H. We could compare trials 1 and 3, noting that the concentration of A and B is held constant, and we varied concentration of H, or we could also compare trials 4 and 5. And so what I decided I'm going to do, because we've got this number sticks out as being really large and looks fun to use, so I'm going to go with the trials 4 and 5 to compare to find the order in H. Now note that the concentration of A is held constant, the concentration of B is held constant, and K is constant, so we could write that the 347.9 over the 21.7, again leaving out the units, is equal to our concentration 0.20 over 0.050, and we said this would be, the order would be given the symbol as Z. So we can take the log of both sides, and we get the log of, let's see, I wrote this down somewhere, the log of 16.03 is equal to Z times the log of 4. Solving this, similar to the way that we solved in the order of A, we're going to find that Z is equal to 2. So now we know we're 0.5 order A, first order B, second order H. Now that we've got that, we can write the rate law, and we would say that the rate is equal to K times the concentration of A raised to the 0.5 times the concentration of B raised to the 1 power. We could leave that out, just have it implied 1, and concentration of H to the second. There's our rate law. Now we're going to use that to solve for the rate constant. Now, since the only trial that we haven't used is trial 3, I'm going to use the data from trial 3 to determine what is the value of K, the last step in this. And so, since we established that we're 0.5 order here, first order here, second order here, we can just substitute this data into the rate law. And so we would have 75.3 molar per second is equal to K times the concentration of A, in this case 0.3, raised to the 0.5 power, times the concentration of B, 0.050, these are molar, raised to the first power, times the concentration of hydrogen, 0.10 molar, and that's raised to the second power. Solving for K, algebraically, we would find that K is equal to 27,500, or something thereabouts. Now, how do we determine the units of K? Well, note that we've got rate in terms of molar per second. So our rate, K, is what we want our units to be. And we're going to multiply that by molar, or by the, sorry, this is the concentration of A. Well, let's erase that. I think I can erase that. Or I can scratch it out. Let's just go with it. This is the concentration of A. that's raised to the 0.5 power. And then we've got the concentration of B raised to the 1 power and the concentration of H raised to the second. So this is going to be molar to the 0.5 times molar to the 1 times molar to the 2, and this is a total of molarity to the 3.5. So that means that K is going to have units of 1 over seconds and molarity, so the 3.5 minus 1, molarity to the 2.5. So we would say that K has units of molarity to the negative 2.5 times seconds to the negative 1. So there we've determined the rate law, and we've solved for K using the differential form. The last, how do we use the integrated rate law? We would see some problem similar to this. Hydrogen iodide decomposes according to the below equation. 2HI produces hydrogen plus iodine. The reaction has a rate constant. We're given a rate constant at 700 degrees Celsius. If the initial concentration of HI in the container is 5.1 times 10 to the negative 2 molar, how many minutes will it take for the concentration to be reduced to 4.9 times 10 to the negative 3rd molar at the same temperature? Alright, so note, we've been given two concentrations, we've been given a rate constant, and we're asked for time. So this right away should just suggest to you that we should be using the integrated form. Now, as I showed in the third slide, that there were various forms that we discussed in class about which integrated rate law it is. And this doesn't say what order this reaction is outright, but we can imply what order it is by looking at the units of K. And if I see units of K having molarity to the negative 1, second to the negative 1, I know that this is a second order rate constant. So that means I should use the second order integrated rate law, which is 1 over the concentration of A at time labeled T is equal to the rate constant times the amount of time plus 1 over the concentration of A initial. All we have to do is substitute our information. Substituting these values, we would say, so if that's our, let's see, if this is our rate constant, this is our initial concentration, this is our final concentration, we would say that 1 over our initial concentration, 1 over the concentration at time t, our final concentration, which is 4.9 times 10 to the negative 3 molar, is equal to K, which was 1.6 times 10 to the negative 3 molar to the negative 1 times second to the negative 1 times T plus 1 over the concentration initial, which was given as 5.1 times 10 to the negative 2. Now, if I evaluate 1 over 4.9 times 10 to the negative 3, I get 204. This would be molar to the negative 1 is equal to the 1.6 times 10 to the negative 3 molar to the negative 1 second to the negative 1 times T plus 1 over 5.1 times 10 to the negative 2 is equal to 19.6. Now I'll subtract 19.6 from both sides and I get 184.4, and this is molar to the negative 1 is equal to the 1.6 times 10 to the negative 3rd molar to negative 1 second to the negative 1 times T divide both sides by that rate constant, and I get t is equal to 115,250 seconds. And the question asked us for how many minutes will it take. If we convert that into minutes by dividing it by 60, I end up with 1,920 minutes. So, alright, so hopefully this provides you a pretty decent explanation of the differential and the integrated rate laws and the different things in which we can do with them. If not, definitely come and see me and ask questions in office hours or go to the tutor room. See you in class.